Thank you very much, and thank you all very much for coming. I'm glad that you're here. Today I am happy that I get to talk about some fun work that we are doing at Facebook. And I use the term "we" loosely. I have not done any of this work, but I work with the people who have, and I'm really proud to be associated with them. These are some, but not all of the names. I especially want to call out Paige Moss. She is a data scientist that has worked with the data and made some of the decisions that we'll talk about as we walk through the data science behind the data for good work. So it won't come as news to any of you, but there are a lot of opportunities to use data to address big problems. Medical needs, public health issues, infrastructure, natural disasters, and we've actually taken a shot at doing some of this. You may have heard of something called Safety Check. What this is for people who have Facebook on their phones. When there is some kind of a crisis and people start talking about it on Facebook, a crisis alert is triggered and people who are in the area are invited to check in safe. So you have the option to say, yes, I'm safe, or opt out, say, I'm not in the area. And at the same time, you get a chance to see how many of your friends are in the affected area and how many of them have checked in safe. So you get to, without sending a bunch of phone calls or a bunch of messages, do a quick finger on the pulse of who you know in your circle that's being affected by this. This is integrated really tightly with something else called community help. So at the time you're invited, you also have access to information about the event. So you can see where it is, roughly the extent of it. You get a chance to see offers for help for whatever your needs are, things like food and water, transportation, baby items. I want to call out animal supplies and shelter are on there as well. So if you're in a place where you need these resources, you can be connected in the moment to people who are offering them. Similarly, if you are in the area or nearby and want to offer these resources, it can be really hard to know who to get them to what to do, who to contact. You can, through community help, offer them as well and make these connections right then, right when it's most needed. You can also, organizations do this as well. So in one organization that we partner with called Direct Relief, here's an example of them offering protective gear to people entering a mudslide area to clean it up. Coveralls, gloves, goggles, masks. So it's a way to, without going out and setting up the infrastructure and establishing a communication network, take advantage of what's there to coordinate cleanup efforts, for instance. We've also partnered with ride-sharing apps to help evacuate people from the path of an oncoming hurricane, to speed up that process as well. And then you're able to also get information about the event. So in this case, for flooding in Peru, you can see some summaries, some photographs. You can get a feeling of the extent, the location, and the severity, and in the moment, use that information to make your decision about how to best take care of you and your immediate circle of people that you care for. In a very exciting announcement just a couple of days ago, a new feature is being added to this, where individual users can add their own photographs, their own status updates, their own observations, crowdsourcing this information gathering. So even further enriching the ability for people in the moment to help others in the moment, in this case with information. Now, when a whole lot of people are invited to check in safe, and some of them do, and some of them don't, that data, when aggregated, gives a picture of what's going on. And you can imagine, for instance, that would be very helpful if I'm an organization like the Red Cross who wants to know where the events are most severe, where people are most in need of help, of shelter, or of medical help. And we partner with the Red Cross and other organizations to do exactly this. So the way this works is individuals who have Facebook on their phone, have location history enabled in their profile, and have location services turned on in their phone, when they are invited to check in safe and then check in yes, that location is noted. And if they don't check in, that location is noted as well. What this gives us then is when it's aggregated up in these little square pixels that you see, there are 360 meters on a side, so roughly a small city block. When they're aggregated up, you can look at the fraction of people who responded yes or no and get a sense of, when this is bright red, nobody invited checked in safe, things are really bad. When it's bright green, almost everyone that was invited checked in safe. There may be help needed, but it's not an urgent crisis in this moment. We can see how this plays out here. There was an earthquake off the coast of New Zealand and the town of Christchurch at around midnight of the event. You can see that it's almost solid brown. So about half of the people invited checked in safe. So something serious is happening. Over the course of the morning to 5 a.m. to 8 a.m., that shifted from brown to green, indicating that whatever was going on there, whatever was happening to help people not feel safe, was somewhat ameliorated. Things had restored to a little bit more normal levels. Also, very useful information. The ability to get this information this quickly and get it into the hands of the people making aid decisions is one of the biggest contributions of this particular work. So, taking a step back to the sophisticated models behind this, we gather up these events, reported checked in or not checked in, for a given event, for a given time window. So this can be 1 hour or 6 hours or 24 hours, depending on the nature of event. All of those reports are added up, just a sum total. For a given area, again, there's these 360-meter grid squares. So for each of these individual grid squares, the total is added up. And the total number of people that are checked in safe is divided by the total number of people who were invited, and that gives a ratio. It can be between 0 and 1. So we have division. That's the extent of the modeling that goes on here. But with that, we get this, really cool picture of what's going on, enough that a decision maker can make a good decision in time to have the desired effect. With this same event, we can see another thing that we get to calculate, which is, this is the town of Kaikoura, which is also in New Zealand, just a little bit north. And if you look at a picture of it, it's a really quiet bay. There's some really pretty old houses. The main industry is hospitality. There's some nice hotels there. One day after this earthquake, we see these red pixels here. So this is a comparison of the current number of people in these areas compared to baseline. Red means significantly lower. So a day after this happened, a lot of people have left. We don't know exactly why or who they were or where they went. We can speculate based on what we know, but we know that there are not as many people there as usual. So this is helpful if you're making a decision. Similarly, when we look at 3 days after, compared to baseline, there's a significant increase in the number of people there and in the surrounding areas. Again, we don't know exactly why looking at this, but we can speculate that people have returned to their homes and perhaps cleanup crews and other aid providers have come as well. So this other quantity that we calculate, this change in population, is of a similarly straightforward nature. For a given event, for a given time window, and for a given one of these grid squares, we compare the number of people who are there on average, baseline, to the number of people who are there at that moment, and then just take the difference and divide to get the fraction. So even with this simple calculation, we're able to get pictures that provide very rich information, most importantly, enough information to make a decision on. To see how this plays out, we can look at a wildfire that occurred in Laguna Verde, Chile last year. Now, if you look at the plot on the left, this represents the baseline population of the area. Dark blue is the highest population density, and there's a little crescent right along the bay of the town center where most of the people live. From there, it fans out up the hillsides surrounding the town to magenta, orange, and yellow represents the least densely populated areas. When we look at what happened during the fire in the plot on the right, you can see the area of the fire. There's a red square there. Presumably people left to get away from the fire. It's a reasonable thing to do. We also see right around it, there are some grid squares that are blue, indicating that there are more people than usual there. So we can speculate that some people evacuated a short distance, far enough to get to safety, but close enough that they could keep an eye on things and perhaps retrieve possessions if the opportunity presented itself. What we also see is down near the town center, we see some blue grid squares there. Possible that people left the fire-affected area and went down to friends or relatives or hotels. Interestingly, we see kind of a diagonal track of blue grid squares out on the water. We don't have enough information to interpret that directly, but it is also possible that that's a ferry route. And so there's more people than average on that as well if they're choosing to leave town and go elsewhere for a while. And then, most interestingly, out on the tip of the peninsula, there's an evacuation point at Playa Ancha University. So also we see an increase of people there, which is reflected in this data. So that's one piece of ground truth that we had that was validated by this data. Not knowing anything about this and then being able to see this plot of where things have changed provides valuable decision-making information. The final quantity that we estimate is people movement, specifically changes in people movement. So while we can estimate the number of people in a location, we can also see when a group of people moves from location A to location B at a regular time on a given day, we can calculate what that baseline is, what those typical levels are. Then during an event, a crisis, we can look at changes. There may be more people than usual making that trip, or there may be fewer people than usual making that trip, and both of those are informative. Those are both interesting. So this is the background is a little pale, but this is Trujillo, Peru, right on the coast. And we can see here during an event that we'll talk about in just a minute, a lot of lines that just spread all over the place. Each of these lines starts and ends in the middle of one of the grid squares that we showed earlier. If there's no change in people movement, then these lines are yellow. If there's more than usual, these lines are green. And if there's less than usual, these lines are red. So what we see here is a lot of red going back and forth. This indicates that from all these locations to all these other locations, there's a lot less movement than usual. I do have to offer an apology if you are red-green colorblind. There are some faint reds and faint greens that might look a lot the same to you. I am, but I've been coached. So to see how this plays out now, how this is calculated, again, this is just what we've seen before. For an event, for a time window, for a start grid cell and an end grid cell, what's the number of people making that trip baseline? What's the number during the crisis, during the current time period? What's that difference and what's the percent change? I just want to take a minute and rather than criticize this approach for its simplicity, I want to celebrate it for its simplicity. When you see a number, you know what that means when you see a result, and you can communicate it to someone even if they don't have a deep math background. So this is an advantage of this type of a simple approach, and this is something that Paige deserves a lot of credit for. So when doing something like this, taking a little step back, there have been several talks during the conference about using data for social good or trying to improve healthcare, in general trying to do something that helps people. Making money helps people, but there are sometimes other more direct ways to help people. Sometimes there are different people we want to help. And the first thing that you want to do to amplify what Kathy O'Neill said this morning is do no harm. So when using the data to try to do something good, make sure you're not doing some damage in the process, which is a lot harder than it sounds. But the most common way to do damage is to violate someone's privacy, to inadvertently connect them with a piece of data that becomes public that says something about them that they were not prepared to say to the rest of the world. So in order to avoid doing this in this case, we have multiple lines of defense. The first is all personally identifiable information is removed. Anything about names, phone numbers, account names, anything like that is removed from these individual events. This is an important step, but it's not enough. There are ways to reconstruct, rematch data with people if you're clever and motivated. And so also, we do temporal aggregation. So as we gather up these events and we assign them to a time window, we add them up and count them up for the time window and then throw away the original information about when exactly they were gathered. So all of these, for instance, 11 events would be assigned to this 9 a.m. time window. It would not be possible to go back and to recreate exactly when any of those occurred. The next line of defense is spatial aggregation. So when these events are counted up over these grid cells, they're summed and that total is represented, but the original information is thrown away so that if you were to take that and you were to try to recreate, well, where did those 11 events occur, you would not be able to do so. And we actually take this a step further. When we assign data to these grid cells, we do a little bit of spatial smoothing, which means we take that count and associate it with the one grid cell, but also associate a little bit with it with the neighboring grid cells. We kind of smear it out just a little bit. This has the effect that then when you want to say, well, where did the events that happened in this grid cell came from, you actually don't even know that they're from that grid cell. So that widens the window out to over a kilometer on a side. So a very blurry, you're looking through a very blurry piece of glass when you're trying to figure out what exactly the details of what are going on the other side, and that information is simply not there to reconstruct. The final line of defense here is this information is not released publicly. It's only released directly to partners that have a track record for using it to do good things, like the Red Cross, the Bill and Melinda Gates Foundation, the World Bank. These are trusted partners, and we work closely with them on this. So to see how this all plays out in an actual event, there was just over a year ago in Peru some unprecedented flooding. They got several times their annual rainfall within the space of just 3 days. And if you're familiar with the topology of Peru, there's a really nice north-south coastline that runs the length of the country. And then from there, the landscape rises steeply to the Andes Mountains that are higher in a lot of places than 14,000, 15,000 feet. And a lot of the sides are unvegetated. So you can just imagine a very steep slope, and you take a big bucket of water and just dump it down, and exactly what you imagine is what happened. Very fast-moving water, not a lot of trees and grass to slow it down or absorb it, turning very quickly into mudslides and to rushing rivers in places where before there was no river at all. There were main streets of towns turned into like very deep, sharp-cut gullies with rushing water at the bottom, people forming human chains to pull individuals out of piles of branches and mud that were on the edges of these rushing rivers, planks strung together over these streets to get people back to their homes, ropes, people kind of passing children hand to hand. A whole village that actually was wiped off the map. After the flooding, there were no structures there or roads or signs of any sort to show that there had been people there. When it was over, almost 100 people died, which is actually miraculously low given the devastation. 700,000 were left without homes. So this was a big event. This is an event for which we used safety check invitations and looked at people, changes in population and changes in people movement with rescue organizations to help provide relief. All of the pictures I'm about to show you, almost all of them, are available on this website. There is a website online. I shared a link on Twitter and Twitter and LinkedIn, if you happen to follow. If you don't follow me, I will share it again after. You'll have another shot. You can go here and you can click these buttons and you can pull up all of these pictures and zoom and pan around and look at these. This is all for you to get your hands on. It covers both the Kaikoura earthquake that we've talked about briefly and this Peru flooding. So this is what Peru looks like broken down by district. You can see the north-south, kind of northwest-southeast coastline on the left. That's the Pacific Ocean on the other side. And then you can see the small districts and the patchy areas. That's where the terrain gets really steep and going up to the mountains. And then just past that, you can see where the districts get large. They're sparsely populated. That gets into the Amazon River basin. That far out, it changes into very large, slow-moving, the Amazon River, and very densely vegetated. So we're focused mostly here on the left side. This is the fraction of people checking in safe one day after the peak of the rains. And so if you look down along the coastline, there's a lot of orange, some yellow, and a fair amount of dark red. This is where the bulk of the population is. So things are pretty bleak there at the moment. One day in, you can see a significant change. So now the colors are still pretty dark. There's still a lot of orange and yellow and still some red, but I'll flip back and forth a couple times so you can compare. So there's the day one, and there's the day two. The day one and the day two. So this tells a little bit more of the story. Things are still intense, but they've backed off just a little bit. More importantly, if I'm making a decision, I need to know where the need is the most intense, where it's the most dire. And we can see, if you look very closely, there are regions where these red districts where no one has checked in safe are fairly kind of clustered together. Those then become targets for providing relief. Now, by the time we get out to day three, we see again that there's a lot of yellow and some orange, still some red, hints of green here and there. But unlike Christchurch, New Zealand, after the earthquake, which within 8 hours had returned back to green, we're still nowhere near that state. Things are still very intense. This also is valuable. rather than taking days or even weeks to do surveys of damage and make decisions based on that, having this right at the moment, 3 days after, really helps make the case for allocating additional resources and helps to get a sense of how big this event was. Now, looking at a change in scale here, the town of Piura, Peru, has its own little story. We can see how this plays out at a smaller scale. So instead of aggregating to the district level, we can look at the individual grid cells here around Piura and the percent of people checking in safe. And because the number of people is not consistent, we'll see some grid cells that have everybody checking in safe. That may have been 1 or 2 people. And one grid cell has nobody checking in safe. That may be 0 of the 1 or 2 people who were invited. So what you get to do with your eye is a little bit of spatial smoothing here and find the trend. But it's not too hard in a case like this, where predominantly it's red. There are a lot of people not checking in safe here. And you can see that around the, getting close to the town center, up there where the name of the town is printed, there's a little bit more variation. Some people are checking in safe, but most are not. So this is 1 day after the peak of the rains. Now, this is informative to compare. So the plot on the right is an example of some of the grid cells for which we have responses back on the invitations. It's not even all of them. But what I want to point out is you can see there are pinpoints on that plot, that data is. And those are aggregated up to the 360 meter level. Comparing this to the Red Cross dashboard on the left, this is what the Red Cross had to work with before using this. So this is not at the district level. It's not even at the level above that. It's at the province level. Very, very coarse indeed, like states, the state level if it was in the US. And so yes, you can see some big trends, but it's much more difficult to make specific decisions about, do I send a truck to this city or to this city? Now we can also look at changes in population. So this is 1 day after the peak. You can see the whole northwest coast has many fewer people than usual. A big depression in population there. This doesn't yet tell us where they went or exactly what their state is or why they're not there, but it shows a big change there. And this adds another dimension. This is not the same place where the fewest people checked in safe. So this adds another opportunity, I guess. A question comes up from this. Well, why are there fewer people there? Why didn't they check in even less safe than people elsewhere? Maybe they were able to evacuate better, or maybe the conditions differed in some way. But it leads to the questions whose answers lead to what help do they need exactly. So the timeliness of this is its key element. It's the thing that helps it to have the biggest impact. Returning now to Piura, which is way up in the northwest. So we can see right around the town center, if you look at the plot on the left, the blue and the purple area shows where the densest population is. So pretty much there's people who live right in the town center, and then a very light distribution of people up and down this valley. When we look at changes in population, blue is more than usual, red is fewer than usual. We actually see that there's a lot of pink and red on average up and down the valley. It's worth looking right at the town center itself because that's where most of the people were. And in that case, we see a small change. It's pretty close to white. It might lean a little bit red, but it's not totally clear. But it has not cleared out. Like most of the people who were there are still there. So what it is possible that from the area, some people were able to leave, but it looks like more of them probably went and are staying in the town center here. Super useful information if you're trying to get them food. And finally, looking at people movement. So we can look at it at a national level here. If you go into the website and play around with it interactively, only changes that are significant over a certain level or that have a certain number of people associated with them are represented. So it ends up looking a little bit sparse. But the most interesting stories come when we look locally. So Lima, the capital of Peru, and one of the biggest cities, is next to an area that contains the town of Chosica. Chosica is one of those areas that had a significant drop in the number of people in it, but Lima not so much. When we look at the trips between the grid cells in Chosica and the grid cells in Lima, we see these bright green, so many more people than usual are moving between them. And together, these pieces of information paint the whole picture. People left to get away from Chosica, and a lot of them went to Lima, to a town center, or to one of the nearby neighborhoods, where they may be staying either with friends and family or in some refugee situation, tents or temporary situation, we don't know. But again, super helpful information if you're trying to provide them relief. And then finally, we're back to Trujillo, Peru. Trujillo was one of the cities that was affected very intensely with its main street becoming a deep gully. And with water moving so much water moving so fast that you could not cross it. Here we see people moving from point to point within Trujillo is almost uniformly less than usual. And in this case, given what else we know, we can put together the story that is because they probably couldn't get from point A to point B with any semblance of safety. So these efforts, on the one hand, there's crisis response, which is safety check and community help. And then on the other hand, disaster maps, which is the population and population movement, or people movement pieces. These are two separate efforts at Facebook that are very highly coordinated, and they cooperate a lot together. That's the website for this interactive display. Like I said, I'll share it online again. And also, feel free, if you want, to reach out and contact disaster maps at fb.com to engage with the team more directly. Now this application is, it's naturally moving, seeing some of the photographs and hearing some of the stories and hoping that something that we did made a difference there, that feels really good. No doubt about that. Taking a step back, there are some lessons that we can take away for our data science activities in general. Good data science is not about using the most sophisticated model. And this is, as someone who loves to play with toys, this is really hard to keep in mind. Deep neural networks are some of the best toys ever invented, but they are not a great fit for every technical problem. Also, good data science is not always about getting the highest accuracy. Accuracy costs. It often requires additional model complexity. It requires additional time, additional computers. It makes additional demands on the quality of your data. And there's just a lot of applications where you don't have that. And that's okay because your end goal doesn't require 3 nines of accuracy. It might only require 80% to do the right thing often enough to be worth it. So maximizing accuracy alone is usually not a good thing to do. However, good data science is about thoroughly understanding the data. To the extent, some of these systems are really complex that we work in, but to the extent that you can know where that data was measured, like what instruments, who did the collecting, what were the conditions, how was it recorded, was it rounded, was there any operation, any cleanup done to it, was there any change in the labeling over time? To the extent that you can get in there and understand where it came from, you can have much more powerful results without even touching a model. That changes your ability to interpret it, which it's hard to overstate how fundamental that is. Also, hand in hand with that, good data science is about asking the right question. also takes a lot of thought. And it's not a matter of willpower, but it's a matter of spending time with the problem, thinking about all of the possible outcomes, talking with the people that it might affect. If you're building something, talking with the people who might use it, and keeping that question that you're trying to answer in mind. And when you get information that suggests you should change it, changing that question and focusing on that, whatever it is, intensely. So thank you. Good luck with your building, especially when you're building things to help people. I appreciate your attention. I'm open for questions. Let's see. So I see a couple of hands. Are we using the mics in the aisles? Okay. So if you have a question, please come and stand behind one of the microphones. We'll alternate this side and then this side. Hi. Yes, please.
I understand that Facebook uses Presto.
Say that again?
Facebook developed Presto.
Uh-huh.
And what I was wondering is, is Presto used at all in the architecture of what you described, or what can you tell us about the architecture?
Unfortunately, I can't tell you anything about the architecture. Like I said, this is not work that I have done. I'm familiar with the results, but not the work under it. I can say that personally, I am a happy user of Presto. For those of you who don't know, Presto is a tool for getting at your data, specifically if it's in an HDFS format, similar to Hive, but in other formats as well. So, sorry I can't provide more information there. Yes?
Hi, two questions. One, how much do you rely on the energy and connectivity grid around the area in the disaster, because those suffer? And two, do you complement this with the typical Facebook data, like people taking images and videos?
Let's see. So I heard your first question is do we also look at any failures of the electrical and connectivity grid? What was your second question again?
Is this safety application correlated with the typical Facebook data when people are in the disaster areas taking pictures and interacting with each other?
Okay, so I'll take those one at a time. I can't say for certain, definitely not this, this effort. Yeah, you know what? Because I can't say I can't say for certain on that. I haven't worked on that team. I'll hesitate making a guess on your first answer. And on your second answer, on your second question, this at the moment doesn't take into account people's individual posts, but as I said a couple days ago, it was announced that those will be incorporated into these updates, and so we'll be able to gather people's individual observations and share them around. So yes, this side.
I am also, I applaud you for the simple model. I think it's a really good idea to...
Thanks, I will pass that on.
But I do have a question about efficacy, because that model doesn't really capture if there's one person responding per geographic area, right? So what are you doing on that front?
Yes, so if there is in this 360-meter grid cell, if there's only one person there and they either respond, I'm safe, or they don't respond, how strong is that signal? You know, maybe they just didn't notice it. And as you can see in some of those plots, there was a lot of bright green next to bright red. How that plays out is you can probably imagine from looking at those plots that we do a little spatial smoothing. We can say like, oh, you know what? Most of the pixels here are red. There's a couple blues. Because of that, I hypothesize, I speculate that it probably should not be used to make decisions about very, very fine grain between, oh, should this city block or this city block get different resources? More on the level of, should this town or this town get this truck full of food? Okay. So, yes.
Thanks for the simplicity of the modelling as well. I'm a Kiwi and was in Christchurch when the earthquake happened. And between when the first earthquake happened and the date that you're looking at, if you'd gone back to the first earthquake, you would have seen potentially less chickens when you're going through, you know, if you're looking at the 350 square metres or whatever it is, in that first earthquake versus the development that's been done for the second earthquake. You saw that there was tiny pieces of red up in Kaikoura because the population up there is very small, whereas you saw a lot of red to green very quickly in Christchurch where the population base is bigger. But from an individual user perspective and the peace of mind it gives your, family, it's amazing.
Oh, I'm happy
amazing.
to hear that. Thanks for sharing that.
Yeah, so no question, but thank you.
Thank you very much. Oh, wow. Yes.
Mine is kind of simple. I was just wondering what the response time on these was, because from a population movement perspective, I don't have any emergency. I can wait to see how people are moving. However, when there's a flood, I think it's kind of a luxury to check in safe on Facebook. So what's the response time and how fast are you able to respond on the response time of the people that get the invitation? If that
You're saying if I'm an emergency responder, like how fast am I able to allocate resources to a location?
One, and from the people within the area that you're waiting to check in safe on, right? So if a flood happens here, you're waiting for me to say I'm safe so that you can determine that, 70% of us here are safe. What's the response time between when the flood happens and being able to check in?
How long do I give you before I say you haven't checked in? That's a good question. I don't know the answer. Yeah. But it's an excellent question. Somebody does. It is just not me. Yes.
Hi. I was just thinking about the socioeconomic effect of this and people who have access to electronics and the ability to check in and use Facebook. And if we're using data like this to make, decisions on resources, but some people aren't represented, is that something that's thought about in this modeling, or do you rely on the NGOs to kind of take that into consideration?
So like for instance, let's say there is an area where there are a lot of people, but maybe they don't have phones. They don't have Facebook.
Yeah.
And so they could be in dire straits and we would not know.
Yeah.
Yeah. So I can't speak to this directly. Based on my other work that I've done on other projects, this is something that we do think about carefully. One surprising thing that I have learned is that phone ownership or access to the internet does not track very well with poverty. And in fact, there are nations, especially in Africa and South Asia, where the cell phone access and ownership is shockingly high across all levels of the poverty spectrum. Mm-hmm. So I haven't seen anything yet that would make me worry about that. But the short answer is I don't know, but I believe that it has based on what I've seen elsewhere.
Thanks.
Yeah, thanks.
Sure. So can you describe kind of what the process would be if a crisis were to happen, about how you actually get this in the hands of decision makers like first responders and those allocating resources? Like, for example, is this something where you call the Peruvian government and get in touch with them and share this with them?
So I don't know the details of it. I do know that it is something that happens between specific organizations that we have a relationship with, and that transfer is very intentional. I don't know what other communication channels there are, but be a good question to dig into to understand this at the next level. Yep. Let's see. No one over here, so whoever's first to a mic.
Any more questions? So one more time, please clap your hands for.
Thank you very much.
Thank you for your presentation.